Okay, so the next problem is one of my favorites. What I love about this is these are very elementary things to state. Some of the proofs are very elementary as well. Some of the proofs are extremely advanced and technical. But these are accessible problems. If you want to try your hand at some open research, there are a couple of things that I've lost the current world record. I would like to get it back. So let me describe the problem. In some sense, it's similar to the circle method. I have a finite set A. So A is a finite set of integers. And I'm going to look at two sets. The sum set and A minus A, the difference set. So for generic A, which set do you think is larger, the set of sums or the set of differences, and why? So if I look at the sums, 5 plus 5 is 10, 8 plus 8 is 16, 5 minus 5 is 0, 8 minus 8 is 0. So whenever you take the same element twice, it's going to give you the same difference, 0, but it will give you new sums. So again, this is the set of all x plus y, x, y, and a. And this is the set of all x minus y, x, y, and a. So using that logic, you would expect the sum set to be larger. But then you think, oh, wait a minute. As Tom Lear once saying, addition is commutative. And so if you remember that, x plus y and y plus x both generate the same sum. But x minus y and y minus x generate different differences. So using that logic, you expect the difference set to be larger. So it was conjectured that almost all sets have larger difference set than sum set. We knew examples of sets that had more sums. And so what kind of metric did we use? Well, let's say our set is all, let's say A is contained in 1 to n, so there are 2 to the n possibles. Okay? The most natural thing to do is to say, I will take each element from 1 to n and assign it in my set A with probability 1/2. If you use that model, we believed that there would be, almost all sets would have more differences than sums as n gets very, very large. Numerical experiments seem to support this, but unfortunately the conjecture is false. Martin and O'Brien proved a positive % of the time you actually have more sums than differences. Their bound was, it was at least, I think, 10 to the negative 7, and we now believe it's about 10 to the negative 3. We're not talking about a large %. It's very easy to be misled with numerics like this. So what I did a couple of years ago with a colleague from grad school, Peter Hegarty, is we looked at other models. And so what we did now is we let Pn be some function which decays with n. And each of these numbers was now chosen to be in the set with probability P of n. And the idea is, if all these probabilities are a fixed positive number, independent of little n, there's going to be so many elements in your sum and difference set that basically every possible sum and difference that could be in there is in there. And what we showed is, as long as P of n is tending to 0, the percent of more sum than different sets tends to 0. So we regained the intuition. What we found, which is truly fascinating, was depending on how rapidly P of n tended to 0, you got different behavior. There was this critical threshold where if it was decaying at a certain rate, you had a phase transition in limiting behavior. So if you're interested, this is explained in our paper in great detail. Some of the decay for P of n leads to very elementary proofs just using Chebyshev's theorem from probability. The more rapid decays require a little bit, the slow decays require a little bit harder analysis and some very heavy machinery. But lots of it is fairly elementary. So we now have a good understanding of what's going on. The next question to ask is, okay, we know there are a positive % of more sum than different sets. Can you give me a way to generate them, a way to find them? And this is where things get very interesting. Until I started looking at this with one of my undergraduates at Brown, basically the best we could do was the number of MSTDs over the number of subsets was something like 2 to the n halves over 2 to the n, so roughly 1 over 2 to the n halves. It'll give you infinitely many, it will give you these large infinite families, but this is very unsatisfying. What I was able to show with my student, and the argument is very elementary, is we got 1 over n to the 4th, which leads to, so I mean, yes, our percent is still tending to 0, but if you basically do everything on a log scale, then you can say, well, it's a positive percent on a log scale. In fact, it's 100% on the log scale. It's a way to make yourself feel a little bit better. I presented this problem 2 years ago, and someone brought this back to, I think, Joe Gallian's REU. And one of the undergraduates, they got very interested in it. And what he was able to do is he was able to replace the 4 with a 1. And so we no longer have the world record. And so the question is, can you do a better job optimizing what is either in my method or what's in his method and actually beat 1 over n? While it would be nice to get 1 over square root of n, that's not going to make me do cartwheels. Actually, nothing will really make me do cartwheels. What you want is to get a positive percent with an explicit construction. You know, is that possible? Can that be done elementarily? If not, then yes, you know, if you can improve the power from 1 over n to 1 over root n, that's an improvement, but it's not fundamentally a new behavior. Going from 2 to the n halves to 1 over n to the 4th 2 to the n, that's a huge change. So there's lots of elementary problems and stuff like this.